This resource is the second of a three-part series that looks at systems of equations. Part 1 defines systems of equations. It then considers the meaning of a solution to that system of equations. It looks at three examples, one of which is a word problem. Part 2 presents the substitution method of solving systems of equations. Systems of two variables are presented, as are special cases for systems of three equations. Part 3 looks at the elimination method for solving systems of equations. Systems of two variables are solved in full. We will also look at elimination for systems of three variables, but in interest of time and attention span, only the beginning steps are shown. Solving a system of equations requires breaking the problem down into a more manageable size. You want to change the problem from two or more equations into or more unknowns into a single equation in one unknown. One method to do so is substitution. The general idea of substitution is to solve and plug in. This works fairly well for systems of two equations, two unknowns, and other certain cases. Substitution is not a recommended method for solving systems of three or more unknowns. How exactly does substitution work? Let's find out. The first step of substitution is to solve one equation for one unknown. This may mean finding the actual number value for the variable, or at least solving for the equation in terms of all other variables. Then you substitute for that variable in the other equation, z. Now you solve for the remaining variable, using a good equation solving algorithm. Now that you know the value for one variable, plug that amount into the equation that was solved for the other variable. Solve that equation. Now you should have the solution for the system. It never hurts to check your answer. We will look at a couple of examples with two variables, and then look at a very special form of three-variable system that can be solved by substitution. For example, suppose you have the system 3x plus 4y equals 70 and y equals 2x plus 1. Upon closer inspection, the bottom equation is already solved for y, because it is already written with y all by itself and all the other terms on the other side of the equal sign. This 2x plus 1 is what we will substitute for y in the top equation. Now we have 3x plus 4 times the quantity 2x plus 1 equals 70. By doing this substitution, we now have an equation completely in terms of one variable. We know how to solve one variable equations, so let's do that. We have to distribute through the parentheses. This leaves us with 3x plus 8x plus 4 equals 70. Combining the like terms, we have 11x plus 4 equals 70. Subtract 4 from both sides. We are left with 11x equals 66. Divide both sides by 11. So x equals 6. We solve for x, but we are not done just yet. We also need to find y, but we can use our original equations to do so. It is easier to plug into the bottom equation, since it is already solved for y. Plugging in, we have y equals 2 times 6 plus 1. So y is 13. To check, we would plug both values into the equation we did not just use. So we have 3 times 6 plus 4 times 13, which is 18 plus 52, which does equal 70. so our answers check out. Now let's look at an example where we actually have to solve for one of the variables. In this example, we have 5x plus 2y equals 43, and 3x plus y equals 24. This time, we don't have one variable conveniently pre-solved for us. But if you look at the second equation, there is a plain y without any coefficients. Let's solve for that y. We are working on the equation 3x plus y equals 24. We want to get the y all by itself, with all the other terms on the other side of the equal sign. To do so, we must subtract the 3x from both sides of the equation. This leaves us with y equals 24 minus 3x. We substitute that into the other equation. So we have 5x plus 2 times, parentheses, 24 minus 3x, close parentheses, equals 43. Distributing, we get 5x plus 48 minus 6x equals 43. Combining the like terms 5x and negative 6x leaves us with negative x plus 48 equals 43. To solve for x, we have to isolate the x term, so we will subtract 48 from both sides. This leaves negative x equals negative 5. Dividing by negative 1, x is 5. Now we can find y. Since we had already solved one equation for y, we will use that form to find the value for y. Plugging in, we have y equals 24 minus 3 times 5. Doing that out, we get y equals 9. Again, we would want to check our values for x and y in the other equation. 5 times 5 is 25, and 2 times 9 is 18. 25 plus 18 is 43, so our answer checks out. This is an example where it makes sense to use substitution to solve a system of 3 equations in 3 unknowns, where the equations look sort of like an upside-down triangle. If we look at the last equation, solving for z seems trivial. So z is 2. We can plug that value into the middle equation. So we have 9y plus 4 times 2 equals 44. Multiplying, we get 9y plus 8 equals 44. Subtracting 8 from both sides, we are left with 9y equals 36. Now we would divide both sides by 9, and we have y equals 4. Now we can plug the values for both y and z into the top equation. We have 3x minus 4 times 4 plus 2 times 2 equals 9. Multiplying, 3x minus 16 plus 4 equals 9. Combining the like constants, 3x minus 12 equals 9. Adding 9 to both sides, 3x equals 21. Dividing by 3, x equals 7. The basic idea of solving systems of equations by substitution is solve and plug in. You solve one equation for one variable in terms of all other variables. Then substitute that equivalence into the other equations. This reduces your number of variables and equations by 1. Continue this process until there is only one equation in one unknown. Solve that equation. Then back substitute to find all the other variables. Substitution works best when you only have 2 equations in 2 unknowns, or really basic 3-variable equations. Either way, you truly want one variable already solved for if you are going to use substitution. The act of solving an equation for one variable in terms of the other can often lead to fractions, which in turn leads to some pretty heinous algebra when you substitute. Wouldn't it be nice if there was another method for solving that avoids this ugly math? There is, but you need to stay tuned to find out about elimination.